looking at lesson 6 today, that is reaction mechanisms. Before we get into the actual mechanisms of a reaction, we're going to look at some terms. I've written these out for you so we can just buzz through them. A reaction mechanism is a sequence of elementary steps that leads to product formation. In other words, a reaction just doesn't happen between, normally doesn't just happen between two molecules banging together and we have products. It's usually more, a little bit more involved than a one-step collision. Elementary steps are the series of simple reactions that represent the progress of the overall reaction at the molecular level. The rate determining step of those elementary steps, there's one step that takes the longest. It is the one that holds things up. All the other steps happen very, very quickly, so we call this the rate determining step. We will abbreviate that RDS. Every reaction has one and only one rate determining step. Molecularity is how many collisions are there in an elementary step. If there's just one molecule, it's called unimolecular. If two molecules collide, it's called bimolecular, and if three molecules have to collide, it's called termolecular. And so that's kind of our lead-up vocabulary that you will need as we work through these mechanisms of a reaction. Now, there are rules that these mechanisms must follow to be an acceptable mechanism, all right? And let's look at that. First of all, the sum of elementary steps must give the overall balanced chemical equation. Okay, we've seen this before in Hess's law. We've seen that we can put together, add a whole bunch of steps, and if in adding those up, we come up with the balanced chemical equation, then those Hess's law have been done correctly. And this is just kind of another application of that same idea, is that when we add these elementary steps up, we need to get the balanced chemical equation, all right? Second, there cannot be an intermediate species, and we'll abbreviate that IS, in the rate law. Right? These mechanisms are what are leading us to write an appropriate rate law. Remember how we said that we don't get our rate law from a balanced chemical equation? We're going to get them from these elementary steps of mechanism. Now, in the rate law itself, we cannot use an elementary step that has an intermediate species. Well, what is an intermediate species? We'll discuss that a little later in context. All right, and finally, you cannot have an intermediate species, but a catalyst in the rate law is okay. All right, so it's okay to have a catalyst in the rate law, but you cannot have an intermediate species. So that tells us it's very important that we know the difference between an intermediate species and a catalyst, which we'll get to a little later. All right, and finally, if a rate law is given, let's save that one. We'll call that 5. Or a mechanism, a series of elementary steps, can only have one rate determining step, all right? And the rate determining step is the rate law, all right? So your rate law will be taken experimentally from the rate determining step, not the balanced chemical equation, all right? Okay, now, if a rate law is given, your mechanism must agree with it. All right? So if they give you a rate law and your rate determining step does not match the given rate law, then it is not an acceptable mechanism. All right? Okay, now a lot of times we'll be using a mechanism to determine a rate law. But then there are times where they'll give you a rate law and say which would be an acceptable mechanism. So these are the points, the 5 points you need to know for looking at and analyzing mechanisms. All right? So let's see how this works. Okay. Here's our first example. We have this reaction. The reaction is R plus S goes to D. This is the balanced chemical equation. This is the reaction. All right? Now they're saying it has this possible mechanism. Is the mechanism acceptable according to the rules that we just discussed? All right, so let's analyze it 1 point at a time. Okay, first of all, the sum of all those elementary steps must give the overall balanced equation. All right, so let's look at that. We've got the first step, R goes to B. And then B reacts with S to form Q. And then Q goes to D. All right? Okay, so let's add this up and see if we get that balanced chemical equation. Well, the B's cancel, the Q's cancel, and I'm left with R plus S goes to D. So yes, point 1, my elementary steps add up to a balanced chemical equation is good. We're good on that point. All right. Now, we also see that it has a slow step and 2 fast steps. Okay? So this is another point. Has only 1 rate determining step, so we're good on that one. Okay? We don't know about the rate law portion of that because we're not comparing. All right, we are determining a rate law from this mechanism. All right, there is no intermediate species in the rate law. Well, once again, they have not given us a rate law to compare to. However, this is where I'll show you how to identify an intermediate species. An intermediate species is something that is formed and consumed. Something that is formed and consumed. All right? Okay, so is there an intermediate species in the rate law? We can say, is there an intermediate species in the slow step? Well, the rate law is from the reactants. We have no intermediate species in the reactant side, okay? So we always write our rate law from the reactants, correct? Okay, so we're good on that. And then I think everything is fine from our rules, all right? The intermediate species, I'm sorry, the elementary steps add up to my balanced chemical equation. There's only 1 slow step. The slow step does not have an intermediate species in it. So the rate law then has to be from this step. So the rate law, rate equals, remember how I said we always start out with, no matter if it's a rate equation, a rate expression, a rate law, all right? We're always going to start with rate equals, okay? And from this one, that would be the rate law for this particular reaction. Notice once again then, this is why we say the rate law is not taken from the balanced chemical equation. It is experimentally determined by analyzing the mechanism, a proposed mechanism. All right? Okay, so what type of molecularity would this particular rate law have? All right? It would have 1. It would be unimolecular, wouldn't it? Right? So this is a unimolecular rate determining step. All right? So this is how we tie those vocabulary words to what we're seeing. All right, so this is an example of where we take a mechanism and determine a rate law for a particular reaction. All right? And this rate law is unimolecular because it involves only one species. Okay? Now, if we're looking at this, it would be bimolecular, isn't it? So whatever they're having you look at is what you say. All right? This would be bimolecular. Now, another thing about an acceptable mechanism, it just has to follow the rules. What is cool is that these intermediate species exist for such a short period of time that we, for the most part, can't even confirm their existence. We do not have the technology available to track something at the level of time that they exist. They exist in like nanoseconds. So in all honesty, all right, in all honesty, you could call B anything you want. You could say, okay, R is converted to gold, and then the gold reacts with S and is converted to silver, and silver then magically appears to D, all right? So are you suspending disbelief and straining your credulity to believe that you created gold and silver? Sure, but is it an acceptable mechanism? You bet, because those intermediate species, we can't verify their existence, so while we can't verify their existence, we could just make something up as to their identity. Now, I don't suggest you do this, but these intermediate species are such, this is why we say they're not the rate determining step. They exist for such a short time. They're so totally, completely unstable that they just, once they're formed, that reaction just goes. All right, so here's an example, our first example of mechanism, how we use a mechanism to determine a rate law for a particular reaction. And we analyze it using those 5 points that we just talked about. Let's try another one. Okay, we have this reaction. A plus B goes to C plus D. Okay, that's the reaction. And it's saying it may have this particular mechanism. A goes to X, X plus B goes to C plus D. All right? And then they tell us this first step is fast and the second step is slow. All right? So now we first say, is this an acceptable mechanism? The first thing I'm going to do is say, if I add up these elementary steps, do I get the balanced chemical equation? A plus B goes to C plus D. Yeah, all right? So far, so good. Okay, does it have one rate determining step? Sure, there's one rate determining step. All right? anything in our rules about doesn't match the rate law are not applicable in this situation because we're using the mechanism to write a rate law, all right? So, however, we cannot have an intermediate species in the rate determining step. So we look and we go, oops, there's an intermediate species in my rate determining step. So am I done? Do I say, you know, this is over? This is not an acceptable mechanism. Okay, well, as it's written, this is not an acceptable mechanism. But we can do something, all right, to make it acceptable. And you're going to notice in your homework packet that there's a couple problems that refer to mechanisms that have this scenario. All right, now, this particular scenario is a little bit higher level, all right? If you don't get this, then you're probably just separating, you know, a low five from a high five, okay? High five. Anyways, all right. Tough to do when there's nobody in the room. All right. But this is this type of mechanism where we have the slow step is not the first step. What happens is this happens so fast that it starts going into a type of equilibrium. It goes into a holding pattern, and it's just sitting there going back and forth, back and forth, back and forth until this kicks it into gear and it can proceed. All right? Because this is going amazingly fast. And as it's amazingly fast and building up that X, we get to a point where then it starts going back and forth. All right? So, because it goes into a type of equilibrium pattern, we can write this in terms of an equilibrium expression. All right, so let's write equilibrium expression for this fast step. All right, and that equilibrium expression would be K is equal to the concentration of X over the concentration of A. All right? Okay. Even though X is an intermediate species and we can't measure the concentration. But bear with me. Mathematically, this will bear out. All right? And so what we're going to do is we're going to take this equilibrium expression. So the first thing that we're going to do, when we are in this scenario where we have a fast step preceding the slow step, my English there, all right? The first thing we're going to do is write an equilibrium expression for the fast step. Okay, so we've done that. Now what we're going to do is rearrange and solve for the intermediate species, or in this case, X. All right, so now I'm going to rewrite this in terms of X, okay? X is equal to, okay, see how I did that? I rearranged this in terms of X. All right? Okay, well, transitive property of math now, I'm going to, third thing I'm going to do is substitute this X into the rate determining step. All right? Now, because this is a constant, it is really irrelevant. All right? So, technically, let's now, here is my rate determining step. Now I'm going to replace this X with this value, all right? Okay, and I'll write it just like that. All right, so now I have a new rate determining step. The rate determining step does not have an intermediate species in it. All right? So now I can write a rate law that reflects this balanced chemical equation from my rate determining step. Now, how do I do that? Rate equals. We always start this out with rate equals, correct? No matter if it's a rate equation, a rate expression, a rate law, rate equals. Okay, now we have the K, all right? From our rate constant, we have the equilibrium K. Don't want another K, do we now? And that is going to be the A, concentration of A, times the concentration of B. All right? Now you're saying, wait a minute, this is weird. Well, a constant times a constant is what? A constant. So this really is not necessary. I wanted to put it in so you can see where we got it, but this really is not necessary. And you can just ignore the K from the equilibrium constant, because mathematically a constant times a constant is just another constant. So that allows us, we have permission to ignore this K. So when you have this scenario where the slow step is preceded by a fast step, that fast step goes into equilibrium. All right, so we got to write an equilibrium expression for that fast step. Okay, we can then solve for whatever the intermediate species is. All right, and then substitute it in, and then we can write an appropriate rate law. Okay, so this is an acceptable rate a mechanism for this reaction. Now notice that this rate law does reflect the balanced chemical equation, but that is a coincidence. All right? So we don't get rate laws from balanced chemical equations. If it happens, it just happens because it's a coincidence, not because it's following the balanced chemical equation. All right. Now, I probably should have done this before we got into the mechanisms, but I want to make sure that we can identify uni, bi, and termomolecular elementary steps. Okay, so let's look at the following on page 14 of your notes at the top. They've given you 3 random elementary steps, and they want to know, are these elementary steps, you know, pulled out of the mechanisms or the reaction? Okay, they want to know, are they uni, bi, or ter? Okay, we always look at the reactants. So in A, we have 2 NOs reacting with 1 bromine, right? So we have to have 3 molecules. See that? We have to have 3 molecules react in this particular elementary step. So this would be termomolecular. All right, B. Now there's something interesting about B. Okay, B obviously only has one molecule right there. One molecule. This is unimolecular. How many molecules, not how many atoms, how many molecules. In this one we have 3 molecules reacting. It's termomolecular. This 1 molecule, it's unimolecular. However, I do want to point out something about this, because I think you saw it on your mini quiz. We don't talk about it much because it's usually used in the context of organic chemistry, and that is the word isomer. Okay, this is not kinetics. This is just that random thing they can still kind of throw in on exam. An isomer, these both are isomers of each other. Okay, an isomer is something that has the same molecular formula but different structural formula. All right? If we add up the atoms, this has 2 carbons, 3 hydrogens, and 1 nitrogen. This has 2 carbons, 3 hydrogens, and 1 nitrogen. They have the exact same molecular formula. However, this particular molecule looks like that. And I'll just tell you now, for reasons you don't need to know for AP, this is a miserable combination. This nitrogen is not happy with 4 bonds, and carbon is just horribly unhappy with that lone pair, all right? And so what happens is that it rearranges itself to a more stable carbon is a lot happier with its 4 bonds, and nitrogen with 3 bonds and a lone pair, all right? But this is an example of an isomer. Okay, they are isomers of each other because they have the same molecular formula. They have a different structural formula. So that is what is meant by isomers. How do you know an isomer? Just look at the molecular formula. All right? If it's different, then they're not. You know, if this had somehow had another H in it, then bam, they're not isomers because they don't have the same molecular formula. All right? So you don't have to worry about what do their structural formulas look like. Just add up the atoms. They're the same. They're isomers. Okay. Okay, and finally, we have in letter C an SO molecule reacting with an oxygen molecule, so that's bimolecular. All right. Now, what we're going to do in the next one, A through E, is say that is the rate determining step. Okay, that is the rate determining elementary step. So I want you to take that rate determining elementary step and first determine if it's uni, bi, or termolecular, and then write the rate law if that is the rate determining step. So A is, uni, right? Because there's just X. If that were the rate determining step, then rate equals, all right? Rate equals, we got the rate constant and whatever's in, whatever reactants are in that rate determining step. B, all right? We have X plus Y, that's bimolecular. If that is the rate determining step, then the rate would be rate equals K. All right? Let's look at C. C has, in this rate determining step of our mechanism, X plus Y plus Z. All right, that's 3 molecules, so that is termolecular. And how would we write the rate law? Rate is equal to X times Y times Z. All right, build some muscle memory with this, because on the exam, when it says write the rate law, people forget about writing rate equals, they forget about the rate constant, and they forget that this is multiplying. All right, so just, this is why we're going through this, so you can build muscle memory, so that you can take and say rate equals. Write this out on your notes. Get the muscle memory. All right. D is X plus X. Okay, we've got X, we have another X. They got to collide, so this is bimolecular. All right. Notice this was written X plus X. It was not written like this, was it? If it was written like this, it would be uni. It is written like that, so it's bi. All right? Okay? The rate determining step. And so the rate law that squared shows us that it's bimolecular, that I've got to react 2 of those X's. That's my rate law. Okay? E we have an X and two Y's. So we have three molecules that have to collide. We have an X and two Y's. All right, so we have three molecules that must collide. So that is termolecular. Okay? And so the rate determining step for this will be rate equals the rate constant times X times Y squared. Right? Now, which of the above elementary steps is least feasible and why? Well, the least feasible ones are these two because they're termolecular. All right? Now, if they are, and generally speaking, if they are further down, if they're in one of those reactions where you have the fast step and then you have to substitute things, that's different. Termolecular is not that uncommon. However, if we have the slow step is the first step, or it's one step, getting three molecules to all collide with the correct orientation, with the correct amount of energy is something tough to pull off. Not impossible, but a little tougher. So termolecular are the hardest to pull off because of the collision theory. The collision theory saying they got to collide with sufficient energy, and collide with the correct orientation. All right? And so if you have a one-step mechanism, very rarely is it going to be termolecular. Okay? If your slow step is the first step, very rarely will it be termolecular. When do we see termolecular? When it is a reaction where the rate determining step is below the fast step. And then we do that thing where we pull in the substitution. Okay? All right. Now, one thing about a one-step mechanism, all right? If all of the above, if A through E were the reaction and not the rate determining step, let's just say A through E were the reaction and the one-step mechanism, okay? Or should I say, let's say that A through E were just one-step mechanisms. Well, we said the rate determining step is the rate law, correct? We also said the mechanism must reflect the balanced chemical equation. So, if we have a one-step mechanism, it will reflect the balanced chemical equation. But once again, it's the cause or effect, all right? It isn't because of the balanced chemical equation. It is because it is a one-step mechanism, and our rules say that our mechanisms must add up, all our elementary steps must add up and reflect the balanced chemical equation. All right, so I'm not contradicting myself, it's just a clarification of the fact that a one-step mechanism, by the rules that we've put for mechanisms, will reflect the balanced chemical equation.